Hello, welcome back to MA211. Let's go ahead and talk about some application problems involving ODEs. This is sort of a classic problem. You've probably seen it, I think, at the end of Calc 2 you saw these kinds of problems. A tank of water initially holds 1,000 gallons of pure water in a tank. You've got some salt solution flowing into the tank. So you've got, this is mistyped. I'm not sure what 10% salt even means. Let's say well, you've got a brine solution containing some amount of salt per gallon. So let's just say that this is 1 pound per gallon of salt. And it's flowing into the tank at a rate of 15 gallons per minute. Now you've got water flowing out of the tank at a rate of 13 gallons per minute. And we'd like to know how much salt there's going to be in the tank at a given time. So I like to draw a picture of these things. You've got a tank here. It looks like this. Somehow you've got salt flow, or you've got a solution flowing into the tank. Looks like that. So there's some water in here. And then you've got a spout at the bottom, and we're losing solution at a given rate. And we know that the solution's flowing in, or fluid in. It's flowing in at 15 gallons per minute. And you've got fluid flowing out at 13 gallons per minute. All right, and you know how much salt is in the inflowing solution. You know that there's 1 pound per gallon of salt in this solution up here. You, of course, don't know how much salt is leaving at a given time. Okay, so we'd like to write down an ODE to describe this situation. On these application problems, what I'm really interested in is, can you set up the ODE? Can you do it properly? Once you set up the ODE properly, I'm fine if you use Maple to do this for the homework. Now on the exams, I'll ask you to both set up the ODE by hand and solve the ODE by hand. But that should be no problem. You have lots of experience solving ODEs like this from the homework. I'm just trying to make things more expedient by letting you use Maple to solve the ODEs. Okay, so let's see. We're going to let A of t be pounds per salt in the tank, pounds of salt. At time t. All right, and we're going to try to quantify how is the amount of salt in the tank changing. So then the big thing that you want to remember when you're doing these salt tank problems, this is very simple. The rate of change in the amount of salt, oops, the rate of change is going to be equal to the rate of salt flowing in minus the rate of salt out. Okay, now this rate of change in the total amount of salt in the tank, that's going to be dA dt. Over here, the rate of salt flowing into the tank. Well, how quickly is salt flowing into the tank? We have fluid coming in at 15 gallons per minute, and we know that there's 1 pound of salt per gallon in that fluid. So salt is coming in at a rate of 15 gallons per minute times 1 pound per gallon. Okay, so that's 15 pounds per minute minus, now how quickly is salt flowing out? Well, we can do a similar thing here. Let's just go ahead and say, I know that fluid is leaving the tank at 13 gallons per minute. So once again, you have a rate of fluid coming into the tank here, and you have a rate of fluid leaving the tank here. Here you have a concentration of fluid in the incoming solution. Now we need a concentration of fluid in the outgoing solution. Now we don't know what that concentration is without knowing how much salt is in the tank. So we can't write down an explicit formula, but we can say that the concentration of salt in the tank is going to be, well, it's A, the amount of salt in the tank divided by the volume of water in the tank. Now, how much water is in the tank at a given time? That's going to be, we start with 1,000 gallons, so it's 1,000, plus you have salt or fluid coming in at 15 gallons per minute. It's only leaving at 13 gallons per minute. So you're gaining 2 gallons per minute, so 1,000 plus 2t. So let me take a moment and I'm going to mark this up a little bit. Choose a color. This is rate of fluid in. So this is a concentration. This is a rate of fluid out. This is another concentration. And that's it. So that's how you set up these problems. So let's see, what's the final ODE that we want to solve? The final ODE is you want dA dt equals 15 minus 13 over 1,000 plus 2t times A. Now on your homework you should say, this is the ODE I want to solve. Draw a little squiggle and say maple. And now get your final solution. Give me just a second to attach the keyboard here. Okay. We'll pull up maple. We want to desolve. We want A to be equal to 15 minus 13 over 1,000 plus 2t times A. Oops. This is A prime. And this is A of t. And our initial condition, if you read the problem, it said we had 1,000 gallons of pure water, so there was no salt at time 0, so we have A of 0 should be 0. And that's it. And there's your solution. That's not necessarily the nicest looking thing in the world, so you'd probably use an eval F to clean that up a little bit. But otherwise, that's it. That's how you solve these kinds of salt tank problems. And we'll do another example here in a minute. But let's just go ahead and continue on and do something else for a little while. So the second problem says we have a cup of coffee sitting on a table. It's initially 95 degrees Celsius. After 5 minutes sitting in a room at 21 degrees Celsius, the temperature of the coffee is 80 degrees Celsius. So assuming that the temperature of the coffee follows Newton's law of cooling, what time will it be 50 degrees Celsius? Now, what does Newton's law of cooling say? Newton's law of cooling applies when you have some object whose temperature change is not going to affect the ambient temperature. Now, of course, that's not correct. If you have coffee sitting in a room, then the heat loss of the cup of coffee does warm up the room a little tiny bit, but we can pretty much just ignore it because it's not very much. So we've got an object, in this case a cup of coffee, an object that's not affecting the ambient temperature. Newton's law of cooling says that the rate of change of the temperature of the object is proportional to the temperature difference between the object and the ambient temperature. Okay, so in this case, let's let capital T of T be temperature of coffee. So what's Newton's law of cooling says? The rate of change of the temperature of the coffee, d capital T, d little t, is proportional to the temperature difference between the ambient, which is 21, and the coffee itself. Now here I have it written as dt dt is actually equal to the temperature difference, but it's not saying that it's equal to it, it's saying it's proportional to it. So it's some constant times this temperature difference. We don't know what that constant is, and it's not given explicitly. Since that constant isn't given explicitly, all we can do is solve that ODE with the constant in it, and then use the information that we're given to hopefully determine what the constant is. So we can use Maple if we're inclined, or by hands, because after a while it'll be faster for you to do it by hand. But I'll go ahead and do it using Maple. We've got to find my pointer. Well, that's interesting. We want to desolve. T prime of little t equals some constant times 21 minus capital T. I didn't have enough parentheses there. And I need a times sign here. There you go. So our solution is capital T equals 21 plus e to the minus kt times a constant. Okay, so obviously we've got to get rid of these two constants floating around before I can use this solution to find out what time the temperature of the coffee will be 50 degrees. What are the two pieces of information I know? I know that at time 0, the coffee is 95, and I know that at time 5, the coffee is 80. So I can use these two pieces of information to find the two constants. So you can use Maple if you want here. Oh no. Sorry about that. So the way I would do it is like this. I want to solve. I can substitute in t equals 0 into this. Well, I'd make an expression first. Capital T is equal to 21 plus a times e to the k times t. Now, if you're not familiar, if I do the substitute command, I can substitute values into that expression. So I can substitute in t equals 0 into capital T, and look what comes out. I get what I think I get. All right, so what I want to do is substitute t equals 0, little t equals 0, into big T. So when I substitute t equals 0 into big T, I need to be getting out 95. And when I substitute t equals 5 into capital T, I need to be getting 80. And I want to solve that for k and a. So there are the expressions that you get. Those are pretty ugly, so I could do an F solve there. Well, that's not working. The other thing I can do is eval F. And there you go. There's the constants that you want. So now you should write that down. A is 74 and K is negative 0.05. That'll probably be good enough for us. Okay, now the problem asks you at what time will the temperature of the coffee be 50. So you want to solve T of t equals 50. Again, you can use maple. So if you're using maple, you could go ahead and say solve. I want to substitute k equals negative 0.05 and a equals 74. You want to substitute those two things into capital T. You want to get out 50. You want to solve for little t. You get 18.74. So t equals 18.74 minutes, and then you're done. All right, so there's a couple application problems. I'll be back with more videos in a minute.